All right, let's dive right in. Today, we're going to pull back the curtain on the architecture of our digital world. We're going to uncover the elegant and, often totally invisible mathematics that's quietly powering the software you and I rely on every single day.
So let me start with a question. It kind of sounds like a riddle. What does a file folder sitting inside another file folder have in common with the concept of infinity? Think about it, right? A folder can hold other folders, which can hold more folders, and it feels like it could go on forever. So what's the connection? Well, the answer gets right to the very heart of how computers handle some of their most complicated jobs.
And this idea, this concept of self-reference, is called recursion. And once you start looking for it, you see it everywhere. It's in a list that contains other lists. You see it in the branching structure of a family tree. And most importantly for what we're talking about today, you see it in a piece of software that literally calls on itself to solve a problem. And yeah, that file folder system, a perfect, everyday example of recursion in action.
Now, here's the thing. While this pattern seems pretty intuitive for our brains, for a computer, whoa, it's a potential minefield. How do you possibly write code that can handle this seemingly infinite possibility without just breaking? How do you create a formal, truly rock-solid language that can define and control these looping, self-referential structures? That's the puzzle we need to solve.
So, the crucial point is this. Computer scientists needed a way to mathematically, model the core building blocks of any program. We're talking about things like loops, choices, and especially that really tricky idea of self-reference. They had to have a guarantee that these things would behave predictably, every single time.
To actually solve this, you can't just work with the code itself. You gotta go deeper, way deeper, into the world of pure mathematics. You have to build a special kind of abstract playground, an environment that has the perfect set of rules, designed specifically to handle the weird logic of recursion. Let's look at how this all builds up. Think of our journey like we're moving down a funnel. We start at the top with those everyday code structures we just talked about. Then we go a level deeper, into more formal algebraic models. And finally, we arrive at the deepest, most powerful level, a concept known as algebraically complete categories.
So, what in the world are algebraically complete categories? Okay, I know, it's a mouthful, but just think of them as that perfect mathematical playground we were looking for. It's an environment that is purpose-built to handle recursive definitions with absolute mathematical precision. This is the arena where we can finally, formally, and safely define those self-referencing data types.
Now, inside this special playground, there's a secret weapon, a key that unlocks this entire puzzle of recursion. It's a very specific mathematical operation that allows this whole idea of self-reference to work in a controlled, predictable way. And here it is. It's called the dagger operation. It looks so simple, right? But that little symbol is incredibly powerful. It represents the actual transformation, the mathematical move that formally solves the problem of recursion. So, what does the dagger operation actually do? Well, it's the star of the show inside our playground. Think of it like an engine. It takes a recursive equation, something that's defined in terms of itself, and it spits out a stable, finite solution. It's the thing that makes the seemingly infinite totally finite and manageable. Okay, so we have our playground, and we have our secret weapon, the dagger. But how do we know exactly how the dagger is supposed to behave? You can't just let it run wild. We need a rulebook. We need an ultimate set of laws that governs not just the dagger, but the entire system. And this brings us right to the core of our explainer today. The original rulebook was something called iteration theory, and it was great. It was awesome for things like loops and choices, but it didn't quite capture the full power of the dagger. So a new, more powerful concept was needed, iteration 2 theories. And this isn't a replacement, it's an evolution. It's a generalization that gives us the specific, nitty-gritty rules for the dagger operation itself.
So what is an iteration 2 theory? It is that master rulebook. It's a formal set of axioms of rules that describes with mathematical certainty exactly how the dagger operation has to behave to work smoothly and consistently inside our playground. This is the theory that finally tames infinity.
And you don't have to take my word for it. This quote from the research really just nails it. It confirms that these rules, these axioms, they perfectly capture how that crucial dagger operation behaves. The theory matches the practice. The map perfectly describes the territory. It just works. Okay, so we've been deep, way deep in the world of abstraction. Let's zoom all the way back out. Why does any of this deep, complex math actually matter? Well, the answer is pretty simple, actually. It is the very bedrock of the reliable software we all depend on. Without these rules, our digital world would be a lot more chaotic.
Look, this framework isn't just some theoretical exercise. It gives us a formal, completely unambiguous language for those tricky, recursive data types. It gives us the tools to analyze incredibly complex structures. But honestly, the most important payoff is right here. It is the absolute foundation for stable, predictable software. This is what guarantees that a function calling itself won't just spiral off into an infinite loop and crash your entire system. It's the mathematical proof that the code will do what you expect it to do every single time.
And that really is the payoff, isn't it? As the source material puts it so perfectly, this is all part of the elegant mathematics that makes software work. It's this hidden, beautiful, and absolutely essential layer of logic that's holding up our entire digital world. So here's what I want you to do. The next time you see a program execute a perfect loop, or you're just clicking seamlessly through folders inside of folders on your computer, just take a second. Appreciate the invisible structure that's happening underneath it all. You can thank a deep, powerful mathematical rulebook that you never, ever get to see. And that leaves us with one final thought. We've just peeked behind one little curtain today, and it really makes you wonder, doesn't it? What other deep, elegant mathematical structures are hiding in plain sight, quietly powering all the technology we use every single day.